So we have seen the complications arising because of the active and passive coupling splittings in the fine structures, and we have seen that the plus minus nature is actually sometimes a disadvantage because there can be cancellations of the peak intensities. The component intensity is in a cross peak, you may lose a cross peak. Therefore, a strategy has to be designed, that was designed in a particular experiment called as J-scale COSY, where you increase the coupling constants along the F1 dimension by using a suitable pulse sequence, by designing a suitable pulse sequence, and that is what is called as the J-scaled COSY. So, along the F1 dimension the J is scaled up, okay. So, here the idea is scale up the J scaled up along F1 dimension. So, I will just show you the spectrum first initially. Look at the spectrum of a simple 2-spin system. This is uracil here. Uracil is a 2-spin system which has 2 protons H5 and H6. So, there is a one diagonal peak and one cross peak, okay. So, I notice here we have the fine structures in each one of these. The blow up of this peak is shown here in a particular peak, that is the cross peak is shown here. Along the omega 2 or the F2, whatever that is, so F1 or F2 what we call it, F2 dimension the splitting is 7.6 hertz, that is a normal coupling constant. Coupling constant between H5 and H6 is 7.6 hertz. Now along the F1 dimension or the omega 1 dimension the separation between the components is 30.4. So 30.4 means this is 7.6 into 4, 4 times it is scaled up, right. So therefore here J along omega 1 is equal to 4 times J along omega 2, this is scaled up, right. So 4 times 4 into that is 4 times J omega 2. Okay. So, this is achieved by design of a pulse sequence. You manipulate your experimental sequence in such a way that the coupling constant appears as scaled up along the F1 dimension, and that pulse sequence is shown on the top there. Okay. So, the normal thing is you have a COSY experiment where you have 2 pulses 90 T1 90, but now what you do is after the 90 you wait for a certain time T1, let us say until up till here. This is your T1 period, you introduce additional delays, additional a sequence tau 180 tau sequence is like a spin echo sequence. Like the spin echo sequence you introduce in such a way that the total time between the two 90-degree pulses is alpha times T1, and here alpha is greater than 1. So the coupling constant is evolving during the T1 period for the period alpha times T1, whereas the chemical shift is evolving only for the T1 period because the tau 180 tau refocuses chemical shift. So what it does? Tau 180 tau refocuses chemical shifts. Whereas the J is unaffected, J is unaffected. Therefore, J continues to evolve for the period alpha times T1. You can choose whatever is the value of alpha, okay. You can choose alpha is equal to 2, 3, 4, 5 whatever depending upon. In certain situations recently I have noticed that people have used alpha of 30, and that is if you have extremely small coupling you want to blow it up in such a large manner that you see the fine structure and the cross peak structure there, and then you can measure the coupling constant very precisely. So this is the demonstration that you have with this sort of a pulse sequence you can get higher resolution along the F1 dimension. It was particularly important to do it along the F1 dimension or the omega 1 dimension because that is where we do not have enough resolution. We are not able to collect that many data points along the T1 dimension as we collect along the T2 dimension. T2 dimension you can easily collect 2048 or 4096 data points, but the same is not possible along the T1 dimension because it will increase your experimental time so much that it becomes quite impractical. Therefore, here you artificially change the coupling constant by designing a pulse sequence so that a scaled up coupling constant appears along this one. Therefore, in this one what will happen is you will have plus minus here, but the minus plus appears at a much larger distance. Okay. So, therefore, this separation is 4 times J and this is just J, this separation is only J. Therefore, the cancellation here is much reduced and you will see a good cross peak intensity in your experimental spectrum. Okay. So, this is one strategy to get over this difficulty of cancellation of cross peak intensities. Okay. Now, let us see some other experiment where you want to avoid the difficulties in crowded spectra. So, what is the crowding that is happening here? Here is a experiment I am showing which is called as omega 1 decoupled COSY. So, notice the pulse sequence here looks very similar to that in the case of J scale COSY, except that this period which was earlier alpha times T1, it is now a constant time period delta, is a constant time period. So, from every FID this period is kept constant delta, which means as T1 increases this starts decreasing, the tau starts decreasing. So, in the previous case as T1 increases tau also increases, so that you have the alpha T1, alpha is greater than 1, therefore alpha T1 this keeps on increasing. The separation between the two pulses continuously increases because you have this whole period was alpha times T1. Here this period is kept constant, this total period from here to here is kept constant. Okay. So, as T1 increases this tau decreases here, so that this period is kept constant. What is the consequence? The consequence is J evolution that happens all the way from here to here is not dependent on T1 at all. So, J evolution is not dependent on T1. J evolution is not dependent on T1. Therefore, what is the consequence? J coupling will not appear along omega 1 axis. Okay. So, this is what we said, whatever was the information during the evolution period will appear along the omega 1 axis or the F1 axis, whatever information is present along the T2 period will appear along the omega 2 axis. Now, you see if the J coupling does not appear along omega 1, what it means? It is equivalent to doing decoupling along the omega 1 axis, it does not show. This is an experimental spectrum to demonstrate that here. So, here is the normal COSY of a particular molecule, it does not matter what molecule it is. You can see this one here. Here is a fine structure, you are seeing a fine structure of a particular cross peak. Okay. Now, here also there is a fine structure, but notice here there are 2 cross peaks here. There are two cross peaks overlapping on top of each other quite close, although they are different, we can see that they are different. There is one 4 here, there is another 4 here, they are slightly shifted along the omega 2 axis. This one is to the left compared to this one here, but there is an overlap here. This overlap can actually cause cancellations of the intensities of the peaks, okay, which indeed has happened. How do you know this? Well, now we do a decoupling experiment, as I said, that you remove the J coupling along the F1 dimension, along the omega 1 dimension. This you are seeing 2 sets of peaks because of the coupling along the F1 dimension or the omega 1 dimension. If you remove this, what happens? See, you get only one peak, one set of peaks which is at the middle of this, which is appearing at the middle. So, therefore, you have no coupling information along this axis, but the full coupling information is retained along the omega 2 axis here. A greater benefit is seen here. You see that overlap which was seen here is removed. You can clearly see that there is one multiplet here, there is another multiplet there. Internally some cancellations have happened, some internally within this multiplet in the second one some cancellations have happened, and this is because of the plus minus character along the F2 dimension, and if they are close by, of course there is a cancellation there. Whereas in this case there is no cancellation, some cancellation is there, but still you are able to see the peaks in the middle, and here the peaks in the middle are gone. So this is the reflection on the magnitude, the relative magnitudes of the coupling constants which I was mentioning to you earlier. Relative magnitudes of the coupling constants changes the peak patterns and the peak intensities, and you can clearly identify that there are 2 spins here, there are 2 protons, fine structure, 2 cross peaks here, and there is 1 cross peak here, and that cross peak fine structure is looking like this. Therefore, this experiment is called as constant time cozy. Constant time cozy because this period from here to here is constant, is kept constant, and because it is also causing a decoupling along the omega 1 axis, it is also called as omega 1 decoupled cozy, omega 1 decoupled cozy or constant time cozy. This is the advantage, and you can get great benefits of this in very crowded spectra. Okay. Now the next experiment which I want to explain to you is called as the total correlation spectroscopy. Now this is actually quite a significant advance, because this will completely eliminate the plus minus character in the cross peaks. This is the cozy here. Okay. Now the toxic spectrum, okay, let us explain the pulse sequence a little bit here. So it goes in the semi, you have the 90-degree pulse, you have the T1 evolution period, and the mixing now is not one pulse but is a series of pulses. There are several, we will not go into the details of those ones, but this is a series of pulses which are nicknamed as MLEV 17. There are 17 pulses here, okay. We will not go into the details of those. This is a particular sequence of pulses, all of them 180-degree pulses. The result of this is we will produce a fine structure in the cross peaks which does not have the plus minus character. It will only have plus plus character both in the cross peaks as well as in the diagonal peak, and you will see many more cross peaks here because of the elimination of the cancellation effects, and you will also have a relay. Okay, what are the differences here? Now I am showing here a comparison of the cozy spectrum and the toxic spectrum here. This is called as total correlation spectroscopy because it shows many more correlations in a given spin system. Okay. Now here is the cozy, which is the one dimensional spectrum of a particular molecule. It does not matter what, I do not even know what this molecule is, but some molecule which has a one dimensional spectrum looking like this, okay, and the same is present here as well, okay, and you have the diagonal which is reflecting this one dimensional spectrum, and you have this cross peaks. So what these cross peaks are telling you? Well, this peak is coupled to this one here, there is a cross peak here. Now here this one is, this proton is coupled to two different protons, one cross peak here, another cross peak there, therefore you are seeing this, and this cross peak is this here, okay. Again you see there is a cross peak between these two, there is a cross peak between these two, this is like the cozy pattern, and this proton here has coupling to this proton here, that is a diagonal is here of this one. It is also coupled to this proton whose diagonal is here. Now we see this is also coupled to this one which is here. So therefore these two protons, those are diagonals are here, they are coupled between themselves. Therefore there is a network of coupling which is indicated by cross peaks. Okay. Now what we saw here, that this proton is coupled to this one there, but this proton is also coupled to this one here, you see, and this fellow has another one here, therefore this diagonal peak is coupled to this proton and also to this proton, okay. So you see how we can identify, and then you go from here to here, you can draw, and this proton is now coupled to not only to this but also to this. So the network of couplings you can establish, how the various protons are coupled in the cozy spectrum, the nearby neighbors coupled in this information you get here. And there is one single doublet here, and that is this fellow. this is coupled to this proton, and that you are seeing this cross peak here, and this one does not have anything else, it has only one. Okay. Now this one however he is coupled to something else, which are these two here. Okay. So this is how we analyze the Cauchy spectrum. Analysis of the Cauchy spectrum in a complex system. See, you could not identify this thing from the one dimensional spectrum. This one dimensional spectrum would not allow you to identify all these correlations. Which proton is coupled to which proton, both are these are proton spectra, okay. All on both axes we have the proton frequencies. So from the one dimensional spectrum you cannot figure out which one is coupled to what. But in this Cauchy spectrum you can figure out the entire network of couplings by monitoring where the cross peaks are. Okay. Now in this case of course the resolutions are pretty good, although the intensity patterns are different in different peaks, and that is because of the magnitudes of the coupling constants, which results in partial cancellations of the intensities of these peaks. Now what is the particular advantage here further? Now you notice here, if we take the same proton, this is the Toxy, you not only see these two as we saw here, okay, those two, you also see some others peaks there, you also see some others there. And why does that happen? Why does that happen? And that happens because of the following. Let me consider a system which is like this, A, M, X, Y and so on, linear system. Okay. In the Cauchy spectrum I see this coupling, I see this coupling, separate cross peaks, and I also see this coupling. In the Toxy spectrum what I see, there is a different color. In the Toxy spectrum I see this, and I also see this, all the three. So from A I will see a cross peak to M, then to X and also to Y. Although there is no coupling between A to X, there is no coupling between A to Y, I still see a cross peak from A to M and A to X and A to Y. This is because of what we call it as the relay. Total correlation, that is why it is called as total correlation spectroscopy. The entire network of couplings will show up in the Toxy spectrum. You can identify by analyzing the Toxy spectrum. So which are the spins which are J coupled in the entire coupling network. Obviously you will have more peaks in the Toxy spectrum than in the Cauchy spectrum. Okay. So now what will be the particular advantage here? One particular situation I will illustrate this to you. What will be the situation? Suppose I consider a spin system which is like this. And this is M X, and I see a cross peak here, cross peak there, and I see a cross peak here and a cross peak there in the Cauchy. Okay. If I see it like this, what it could mean is that there is an AM cross peak, there is an AM coupling. This will tell me that there is a AM coupling, but there is also a cross peak from the M. But however, suppose there are two protons M and M prime overlapping. Let us say there is M and M prime here. They are at the same chemical shift. Now if AM coupling, but if there is a M prime X coupling but there is no MX coupling, there is no MX coupling but there is an M prime X coupling. So I see a cross peak from M to X, but this can as well be an M prime X coupling, M prime X cross peak. So how do I figure that out? So Cauchy will not be able to tell me that information. Okay. Now if I do a Toxy of the same, I have the diagonal here, this diagonal, same as before. Now if I have a peak here which will be there in the Cauchy, I will also have a peak here as in the Cauchy, but if it is AMX and not AM plus M prime X, if it is an AMX, I will see a cross peak here in the Toxy. but if it were AM plus M prime x, then I will not see. This will be AMX, this will be AMX and not AM plus M prime x. So this is not true, okay. So therefore this I can eliminate this in the Toxi spectrum. This is the Toxi. So in the Toxi spectrum I will see this additional peak if there is a AMX system and not AM plus M prime x, okay. So therefore that is how this experiment is useful to figure out if there are overlapping peaks and you make a mistake in your connectivities in the analysis of the Cauchy spectra, okay. The second important point here is all the peaks will have in phase character. Another important factor which I should mention, that all the peaks are plus 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 plus. There is no plus minus at all, okay. So therefore there is all in phase, this is called as all in phase, all in phase character in the Toxi. In the Toxi all the peaks will have in phase character, that is plus 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 or minus 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 minus, whatever you want to call it, because that is but there is no plus minus plus minus. Therefore there will be no cancellation of intensities, okay, and that is an important factor which is extremely useful because there is no loss of intensity. It is not so much dependent on the magnitudes of the coupling constant, although to some extent it does, because this what we call as the mixing time here, the mixing time depends on what is the coupling constant you should use. So how much is the mixing time, and that is this is called as a mixing time. Suppose I say tau m is a mixing time, okay. This depends on the ranges of the coupling constants. So what are the important messages to take here? In the Toxi spectrum there is a relay of information through the coupled network. All the cross peaks have in phase character and all of them are absorptive in nature, okay, and all of them in phase absorptive. Okay, therefore there is no dispersive character at all. So the resolution here is much better than what you have in the Cauchy. So notice here this is true for both the diagonal as well as the cross peak, okay. Therefore the diagonal is also pretty clear. The peaks which are very close to the diagonal can also be resolved in this Toxi spectrum. Therefore these days whenever you have a molecule you straight away record a Toxi spectrum, but only certain situations you want to remove certain number of peaks and be more specific with regard to the near neighbor interactions, then you will use the Toxi spectrum and then you will use the Cauchy or the double quantum filtered Cauchy, okay. So this sort of experimental techniques one can use to obtain the relevant information in your space system, okay. So we will not go into the details of this mixing sequences here, these are quite complex and this involves a series of pulses, several pulses, and all the other characters with regard to the data collection, the resolution, etc. will be the same as in the case of normal 2D spectrum, other 2D spectrum, okay. Now this brings us to another important experiment and that is called as the NOESY. So we will only make a small introduction to this, we will take up this in greater detail in the next class. This is again an extremely important pulse sequence and this is extremely useful for determination of the structures of the molecules, macromolecules, the proteins, nucleic acids. This experiment is also called as XE, this is also called, that means exchange spectroscopy, or it is also called NOESY, this NOE correlated spectroscopy, and here you have completely different principles of magnetization transfer. In the previous cases we had actually used on the basis of the J coupling. The J coupling was the driving factor for all of these ones. Okay. Now there are other mechanisms of the transfer of information, and that happens in the case of the NOZ or the X-ray spectra, and this we will take up in the next class. Okay. I think we can stop here.